Okay, topic 4.3 covalent structures, part 2. These are just a few things we didn't get to when we first covered covalent structures. Okay, resonance structures. A molecule or polyatomic ion that contains a double bond that can be placed on more than one atom. So you've seen this before. So for example, ozone. Well, ozone has two oxygens that are double bonded, but that double bond is not locked in place. You don't have a double bond between these two oxygens and a single bond here. That double bond is distributed evenly between all the oxygens. If you were to measure the bond strength, you would find that the strength is halfway between a double bond and a single bond. And actually, in our next unit, we'll talk about what's called bond enthalpy, the amount of energy necessary to break a covalent bond. And for ozone, it would be halfway between a double bond and a single bond because we have resonance. When you are asked to draw resonance structures, you simply draw all possible structures, like for ozone, these would be the two possibilities, and we use a double arrow to indicate the resonance going back and forth, back and forth. Let's do an example, a practice problem. Draw the resonance structures for nitrate. So you can try this yourself. Pause the video. I will do it in 3, 2, 1. This is the Lewis structure for nitrate. The double bond there, however, could be on the other two oxygens as well. So we simply draw all possibilities. So the double bond is now on this oxygen, and then here the double bond is on this oxygen. And double arrows again, indicating that it resonates back and forth, back and forth. You can't draw resonance structures without a two-headed arrow or two arrows. Now, while we're talking about resonance, it seems like it's a good idea to throw in here at no extra charge benzene. Benzene is a very, very common molecule. You see it all the time, particularly when we get to organic chemistry. And what it is, it's 6 carbons in a ring with alternating double bonds. So you can see every other carbon is double bond. And the double arrow here indicates that that double bond is rotating around. You can see you have a double bond here, single bond here, just rotates around. Now drawing the benzene ring like this is a bit of a pain. Rather than drawing it like this, we typically draw it as a hexagon. And you can see that the double lines here indicate an alternating double bond. Now in organic chemistry, we'll talk about this, but just real quickly, the way that we draw organic compounds using what are called line structures, we literally don't put in the symbol for carbon or hydrogen. Every intersection, every point is a carbon atom, and if anything else is going on, then it's drawn in. So for example, this carbon is double bonded to this carbon, so another line goes in here. And then we know that carbon always has to have 4 bonds. So this carbon has 1 bond to this carbon, 2 bonds to this carbon, and so what's missing is a bond to hydrogen. And so that's the hydrogen there. So we just simply don't draw that in. Anyways, I just wanted to point out this is how we draw benzene. But this is a more common way of drawing benzene, where rather than having alternating double bonds, we use a circle to indicate resonance. The inner ring is used to indicate resonance. So this is the simplest way of drawing the benzene ring, and it's a simplification of this. And again, I'm only bringing this in because you see this all the time, and I thought some of you might be interested in what that ring means. It means resonance. This is the way that you most often will see benzene drawn. Note, the carbon-carbon bond length and strength is in between a single and a double bond, just like ozone we were talking about before. You don't have a single bond and a double bond strength. You have halfway in between the two. This is a nice diagram of what's really going on. These are the p orbitals that are responsible for the double bond between the carbons. And they exist both above and below the plane of the benzene ring itself, which you can kind of see here. The lobes of the p orbitals overlap one another, and you have the electrons resonating both above and below the plane of the benzene ring. Nice little diagram. Dative coordinate covalent bonds. You'll hear the term coordinate used a lot. IB prefers the term dative. When one atom supplies both electrons to form a covalent bond. So the example that's always used is boron trifluoride and ammonia. Well, remember boron is an exception to the octet rule. It will have only 3 pairs of electrons around it, but it has an empty p orbital, just a p orbital with nothing in it. So what will happen here is ammonia, that lone pair of electrons on the nitrogen, will go and merge with that empty p orbital. And so the empty p orbital from the boron and the filled p orbital of nitrogen will merge together to form a covalent bond. And there's a special way we denote that. That's with an arrow. So this arrow here is just a covalent bond, but the significance of the arrow is it's saying that it is a coordinate covalent bond where one atom supplied both electrons. And the tail of the arrow always is from the atom that supplied both electrons, and the head of the arrow is the atom that accepted that pair of electrons. Okay, so that is our dative coordinate covalent bond. So an animation of this, and you can see how the orientation around boron shifts as that lone pair comes in. The Vesper model at work. Practice. Show the formation of a dative covalent bond that occurs when water reacts with a hydrogen ion. Now remember, a hydrogen ion has no electrons. Hydrogen atom just has an electron and a proton. Remove that one electron and we have just a proton. And in fact, a hydrogen ion is referred to as a proton for a good reason. Well, in order for a covalent bond to occur here, oxygen needs to supply both electrons. Now, the hydrogen still has its s orbital, it's just there's no electrons in it. So once oxygen supplies both electrons that are needed, you have the s orbital of the hydrogen overlapping with the p orbital from the oxygen to form that covalent bond. It's important to note that the covalent bonds here, even though we use an arrow to represent that a coordinate covalent bond formed, are exactly the same. They are identical. There's no distinction between these covalent bonds. They're identical. All right, and this is our dative covalent bond. I'm going to show you a video, one of the IB review videos. He does a really good job of going into how we can, simply by looking at a chemical formula or a Lewis structure, determine if we have a dative covalent bond in that structure. So I suggest that you take some notes.
What are dative covalent bonds? Well, first of all, let me draw out a water molecule using the Lewis structure. Oxygen's in group 16, so it has 6 valence electrons, represented by those dots. And hydrogen's in group 1 valence electron, represented by the crosses. The 2 bonds that I've circled there, made of a dot and a cross, are regular covalent bonds. An electron from each of the atoms is shared in this bond. And the 2 I've just circled at the top there are lone pairs. Both electrons in a lone pair are from one atom. Now, if I bring in a hydrogen ion, that's a hydrogen atom that's lost its electron, it can actually turn that lone pair into a dative covalent bond. So a dative covalent bond is where both electrons in the bond are from only one atom. So I've just made the hydronium ion, H3O+. So how would I draw this out? Well, the dative covalent bond is drawn with an arrow. Not just a line, but an arrow. Don't forget the square brackets and the plus as well. And it behaves just like a regular covalent bond, except that both electrons in the bond are from only one atom. Not one from each atom. Okay, let me draw out the ammonia molecule and now bring in a hydrogen atom. Now notice there's 3 electrons there trying to make a bond, and that's not going to happen. Only 2 electrons in a bond. And so this will only work if I add, again, a hydrogen ion. I don't want that extra electron. I just want an H+ to be added. a dative covalent bond is formed, and now this is the ammonium ion. So the ammonium ion has to be NH4+. It can't be NH4. I need to lose an electron somewhere along the way. This is the hydrogen cyanide molecule. Hydrogen cyanide smells like almonds. Marzipan smells like almonds. Semtex plastic explosive smells like almonds and looks like marzipan. And almonds smell like almonds. So just avoid almonds. If I draw boxes around each atom, see hydrogen is in group 1, it has 1 electron from itself. Carbon group 14 has 4, and nitrogen group 15 has 5. So there's no dative covalent bonds there. Every electron can be allocated to its parent atom in the bond, like I showed. But for carbon monoxide, if I draw out the Lewis structure for that and put the boxes around, each atom is apparently involved with 5 electrons. And that can't be true. Carbon's in group 14, it can only put 4 electrons into the Lewis structure. And oxygen's in group 16, it can only put 6 in. So there must be a dative covalent bond. Indeed, in green are the 6 electrons from the oxygen. So once again, let me show you how to draw it out. You put an arrow for that dative covalent bond. It behaves no differently to regular covalent bonds. Carbon monoxide will also asphyxiate you, just like cyanide, but it doesn't smell of almonds. So now I'm worried if there's no smell. Some quick questions. Can you draw these out and find the dative covalent bonds? There's one there. Boron has 3 electrons, so that must be a dative covalent bond from the nitrogen. And oxygen, 6 valence electrons, so also another dative covalent bond from the nitrogen.
Okay, that is the end of covalent structures, part 2, end of notes.